This is a video for AQA Further Pure Mathematics, Calculus section 5.5, using substitutions of the form x equals a sine u or x equals a tan u. Well, in previous videos you've seen that where we've used the substitution x equals sine u and x equals tan u, when we've got expressions such as the square root of 1 minus x squared or 1 plus x squared. Sometimes we have to use substitutions where we've got a factor in front of the sine or tan. So for example, x equals a sine u and x equals a tan u. This means that, for example, we've got our expression cos squared u plus sine squared u is equal to 1. But if we put a factor a in front of that, we get a squared cos squared u and a squared sine squared u is equal to a squared. And hence you can see how this may help in the integrals. So let's look at a couple of examples using this. In the first one, we've got 25 minus x squared rather than 1 minus x squared. So here the obvious substitution to try would be x is equal to 5 sine u. And then when we differentiate that, dx by du is equal to 5 cosine u. It's a definite integral, so that we need to change the limits, and when x is equal to 0, we can see that u must be equal to 0, and when x is equal to 5 over 2, then that means that sine u must be equal to a half, which gives u is equal to pi by 6. Again, remember, must be radians. So making those substitutions, then our integral becomes an integral from 0 to pi by 6 using the limits for u. And then we've got the square root of 25 minus 25 sine squared u, and then multiplied by the dx is going to become 5 cos u du. So we've got 5 cosine u du. Now the bracket there, 25 minus 25 sine squared u, of course, is just equal to 25 cos squared u. So when we take the square root, that's 5 cos squared u. So in total, then this becomes 25. So we've got 5 multiplied by 5, and inside an integral cos squared u du. We need to use the identity for cos squared. So cos squared is a half of cos 2u plus 1, so we can substitute for that. The half comes outside the integral, and then inside we've got cos 2u plus 1 du, and still our limits 0 to pi by 6. This gives 25 over 2, and when we've integrated, cos 2u integrates to 1/2 sine 2u, and 1 of course integrates to u, evaluated between 0 and pi by 6. Substituting in the values gives sine of pi by 3 as root 3 over 2. So we get 25 over 2 and then root 3 over 2 multiplied by a half, and then plus pi by 6. When we put 0 in, both of those become 0. Let's just look at that on this slide here. So we can see that the substitution there, 5 sine u rather than just sine u, because we've got 25 here. And then the substitution goes very similar to ones you've had before. At the end, got our substitution sine 2u when we've done the integral and putting in the limits pi by 6, giving us then the root 3 over 2. The halves come outside the bracket there, so that inside the bracket we've got pi over 3. In this second example, we've got 1 plus something x squared here on the bottom line. So this is going to be a tan type of substitution that we're going to use here. But because we've got 1 plus 9 9x squared, then to make it 1 plus tan u, we need to substitute not just x equals tan u, but x is equal to 1/3 of tan u. Then when you substitute x squared, that's going to give the bracket there 1 plus tan squared u. So if x is equal to 1/3 tan u, then dx by du is equal to 1/3 sec squared u. And so making the substitution, the integral, which is 1 over 1 plus 9x squared to the power 3 over 2 dx becomes an integral of 1 over 1 plus 9 times x squared is just 1 plus tan squared u, so 1 plus tan squared u, and that's the power 3 over 2, and then we've got 1/3 sec squared u du. But 1 plus tan squared is equal to sec squared, so we've then got 1/3 coming outside the integral from here, and then sec squared u divided by sec squared to the power 3 over 2, so that's sec cubed u du. So in total we've got 1 over sec, and of course 1 over sec is equal to cosine, so we've got 1/3 cosine u du. So there we are, we've proved what we wanted to do, and so we can then go on and integrate this quite straightforwardly. The integral of 1/3 cos u, of course, is 1/3 sine u plus c. But now what we're going to do is to go back and get a function of x. So our transformation was x equals 1/3 tan u, so we can say that 3x is equal to tan u, and we also know that sec squared u is equal to 1 plus tan squared u. So therefore we need that sec u must be equal to 1 plus tan squared, so that's equal to 1 plus 9x squared, and then the square root of that. If that's sec u, then cos u must be equal to 1 over sec, which is 1 over the square root of 1 plus 9x squared. So now we've got expressions for cosine u and tan u, and we can use those to give sine u. So we're going to use the fact that sine u is equal to the tangent divided by, sorry, I beg your pardon, tangent multiplied by the cosine. So that sine u is equal to tan u multiplied by cos u. So that expression at the top, the integral, which remember started off as the integral of 1 over, and then we had 1 plus 9 x squared to the power 3 over 2 dx. We've shown it's equal to 1/3 of, and then sine u is tan u multiplied by cos u, so that's 3x divided by the square root of 1 plus 9x squared. Of course, the 3's will cancel out of that to give you x over root 1 plus 9x squared. So just have a look at this final one to finish off with. Note that this method here of using the tangent to give tan is sine over cos, and the fact that sec is 1 over cos is quite common in this type of example. So do make sure that you understand what's going on in this section. Well, that concludes this particular video, other than to go through as a summary of what we've done. So over the last few videos in this series, we've been looking at these substitutions of using sine u and tan u. And in general now, we've looked at cases where we've got a sine u and a tan u. So they will result in integrals which may well need other techniques. So we've used today the double angle formula. And also you have to take some care in this transforming back to the original variable. If you're using definite integrals, remember that the easiest method is to make sure that you also transform the limits and substitute those into the integral when you found it. Well, so this completes the series of videos on further integration techniques.